Hi, I am Juan Adolfo Grijalva Delgado. I am going to present to you my work thesis, which is a development of low-cost IoT weather station for environmental monitoring in urban arid environments. This is to major as an electronic engineer. My Itsun advisor is Dr. Ian Mateo Sosa Tinoco, as well as Dr. Luis Mendez Barroso, and we start. So this is the layout of the presentation, pretty usual. We'll start with the background. So we have that a weather station is a tower or a system that has, first of all, has a data logger, which works as the brain of the system, and then it has a variety of sensors connected to it, which measures multiple weather variables. It could be temperature, humidity, pressure, wind speed, etc. With this, we need to understand what is the Internet of Things, IoT. This is when we have devices connected to the internet. It could be a sensor, multiple sensors, or as in this case, a system connected to a local or a cloud server. All right, so now uh, the problem and objective. Uh, these weather stations that we talked of, they're usually very expensive. They're pretty high cost. They usually go around $5,000, which is around 100,000 pesos. And those are the basic ones. If we want to measure more variables, or we want higher end sensors, it goes even higher. The price goes even higher. So in this work, we're trying to validate the accuracy, the durability, and the cost of a low cost weather station, and how this compares to a professional grade station. In this case, we're comparing it with a Campbell scientific weather station. So, as mentioned, objective is to have a low cost, accurate, and a durable weather station. These are the main objectives of this work. We have the method route. As usual, you design the system, you select multiple sensors, you test them out, you choose and pick which one works, which one doesn't, and you implement it all together. You try it out, you test it, and repeat that until you get the right desired result, and then it is installed in the area, the study area, and data is collected. Now we have the development of this work. So this work is separated in three parts: data transmission and storage, the sensors, and also the power system. So as we can see in this diagram, we have the sensors, data logger, the power system, and it uploads to three different places. First of all, it uploads to a cloud server, which in this case is a Google Drive Sheets, which is kind of like a Microsoft Excel sheet, but in this case, Google Drive, which is a cloud environment where anyone can access to it. And also, data is uploaded to an app through Blink. It's a Blink app. It is a open environment where you can program the app. And also data, as this is a redundant type of system, it is uploaded to an SD memory just in case data is lost or Wi-Fi connection is lost. We'll look at the schematic and the physical board. We see we have an ESP32 microcontroller. It has Wi-Fi and Bluetooth capabilities. It has around 32 pins. It works around 4 megahertz, and so on. Usual microcontroller. The sensors that we have here, first of all, temperature and humidity, which is the ACE-HT10. It measures temperature and humidity. It gives a digital signal. We also have an analog anemometer. This one measures wind speed. We also have a barometric pressure sensor, which is called the BMP280. You can also measure temperature, humidity. And finally, we have a tipping bucket. In this case, we have a Texas Electronics tipping bucket. It is not a low-cost sensor. It is a high-end tipping bucket because we couldn't find a low-cost version that met with the requirements. Therefore, we had to use this high-end tipping bucket. We can also see the power supply, the power system. We have a 20-watt solar panel connected to a 12-volt, 7 amp, 4 amp lead acid battery, and the charge controller for both of these components. We also have power regulation, voltage regulation for the 12 volts. It goes down to 5 volts and then it goes down to 3.3 volts. So on the right side, we can see the PCB, which I designed, and it was manufactured in China, and it was installed for the weather station. We can see also the SD card module, where we save data. We can also see the RTC module, which is a real-time clock. It's the DS3231. Now, we installed the weather station on the roof of a building in Itzon Centro. So we have the low-cost weather station, which is we call Gila, as the Gila Master. We have Gila installed in one roof, and parallel to it, next to it, it's another building where we have the high-end Campbell reference station. Therefore, we can have it really close. They'll have the same environment, measure the same variables, and that way we can compare it as close as possible. On the right side, we have the cloud server that I was speaking of. It is on Google Drive. It uploads data every hour. Every hour. It measures every 5 seconds, and it gets the mean of that and uploads it every hour. Now, results. So here we have 3 years of data, which is more than 17,000 data points, or 17,000 hours of data. We can see we have temperature, humidity, wind speed, and barometric pressure. This time series is more to see the behavior of these sensors and the durability of these. So we can see there's a few gaps on the time series. This is either for maintenance or some type of faulty error. And we can actually see the anemometer had a big gap. This is because there was a period where either dirt or humidity or water from the rain, it accumulated on the rotating part of the anemometer and it stopped rotating. Therefore, we had to fix this with some lubricant, and it continued working. Here we have the correlations diagrams of each variable. On the x-axis we have the low-cost station. On the y-axis we have the reference or the Campbell station. So first we have temperature. On the top left we can see it has a pretty high R-squared of 0.99, which is almost ideal. We can see the temperature was actually being undermeasured by a little bit at high temperatures. Meanwhile, on the low temperatures, it was actually very accurate. Next, we have humidity. So in humidity, we have a pretty linear, constant level. It was always measuring under we have an R square of 0.98, which is very close, very good. Now, these two are the same sensor. Now we're moving on to the next sensor, which is the anemometer, wind speed. This one had the lowest correlation with 0.9. We can see it was always measuring um, under compared to the reference station. Next, we have the barometric pressure sensor. We can see the low levels it was measuring under, and on the high levels it was measuring above. And we have a R square of 0.93. Now we have statistical metrics. We already talked about determination, R squared, and correlation, R. We can also see we have the root mean square error, which is RMSE. The higher the level of RMSE, it means there's a higher chance of error when trying to predict future measurements. And we see we have the highest on humidity and actually the lowest on wind speed, which speaks it is constant. We also have the bias. This one tells us either it was measuring under or above. We see temperature was the only one that was measuring above, but very close to the one, which is very ideal. And barometric pressure, since it was isolating between under and above, we get a very close value to 1. And the most important thing is that we have in all the variables, we have a p-value of under 0.01, which this proves to prove our hypothesis of looking for sensors that measure very closely to the reference. So that is a very good result. So now we have conclusions of this work. So looking at the past data that I just spoke of, it measured very closely to the reference station. This is a very good indicator. That means we can trust the data on these low-cost sensors. Nevertheless, we did have issues on the durability of these sensors. It required maintenance throughout the whole experiment. We had to go up there and check on it, clean it up. And one example is the anemometer that got dirt and water stuck on it that had to be fixed. And also we had a lot of issues with the battery. We didn't install it properly. Therefore, we did have a few issues. We had to exchange the battery a few times. So that was an issue. So for future works, we would have to have a better installation of the battery, probably a better box where we can have the data logger and the battery system in one single box, have it protected. Also, as future work, we can probably develop some low-cost tipping bucket that can be recreated and be as accurate or as good quality as a high-end tipping bucket. And also the cost, I forgot that, the cost, we actually got it around $1,000, which would be a fifth of the price. We mentioned the high-end stations cost around $5,000, 100,000 pesos. Meanwhile, the low-cost station cost around $1,000, which would be around 20,000 pesos. That means we can build a network of 5 low-cost stations for the cost of one professional-grade station. And that would be it for me. Thanks for listening.